Then next, I want to talk about the bare minimum that we need of probability theory. So I'm calling it the absolute essentials of probability theory. And many people find it boring because it has to do with distributions and so on. But the concepts that I want to discuss next cannot be understood without these notions. So what we need is the notion of random variable, or more generally, of random element. Who has heard of random variable before? Okay. So a random element, in spite of its name, is a deterministic function. And that many people find confusing. Yeah, it's called random variable or random element, but it's a deterministic function that's defined on an event space. And we can then, it maps the outcome of a random experiment and that's defined as an experiment that may have different outcomes under identical experimental conditions. Two, either a real number. It's a very long sentence. I will go over it again. Which is called a random variable. So you have an event space with different possible outcomes, and you then have some domain, let's say the real line, and this maps, this random function is a deterministic function that maps each outcome to a point in this domain. And it need not be IID. So, it need not be, what's this, bijective. So different points, different outcomes can be mapped to the same value. So let's say if you throw 2 dice, then and your random variable is how many eyes have you observed, then there are different outcomes that give you the same number of eyes. So this is just a scalar number, but sometimes random experiments give not a scalar number, but a whole set or a vector of numbers. That would be a random vector. If the set of numbers is indexed by continuous space or time, this is called a stochastic process. And this is often depicted in the following way, that we have an event space, and let's say a temporal process here. Then this event would be, this function here, and the next event would again be an entire function, and so on. This is now time. So these things have, you could write them with two indices, one index that says which outcome it belongs to, and another index that says where in time are we looking at, if you want to get a scalar number out. Or you could have a set of numbers indexed by two or more, not continuous but discrete spatial dimensions. This is then called a random field. And that is an extremely important model in image analysis, as you can imagine. So we would have a discrete set of points, for example, the pixel locations in an image, and we would then have different values for each pixel. That would be a random field. Or, and this is where it gets really interesting and where we are actually quite close to the forefront of research and probability theory, you could have random elements that are trees, graphs, etc. These are different in the following sense that, if I have a vector of numbers, or if I have a random field of fixed size, I always get the same number of numbers out. So for instance, a random vector of length 20, so each time I press the button and get a new random vector, it has exactly 20 numbers. But if I start producing random trees, these can be of different size. So one could be this, one could be that. There's no way of predicting what they will look like. So these are somehow, these are somehow, in essence, these are more interesting structures and accordingly hard to deal with. Now, the most frequently used term, however, is really the random variable. And this is often abbreviated as RV. And if people don't want to talk about random element and all that, they often say random variable even if they mean a vector or a random field and so on. Okay. Notationally, it is usually represented by an uppercase symbol. So your typical random variable is called x. Yeah. And realization. For example, the number 2 is then represented by the corresponding lowercase symbol. And well, we need that because to understand the funny notation that statisticians use, or sometimes funny. So that was for notation or terminology. And random variables induce a probability distribution, another technical term. On their range. Now we have to distinguish between discrete and continuous distributions. Discrete distributions assign positive probability to at most countably many different values in the range. So these are discrete distributions, and these sets of values are then called probability functions. I'm underlining all the technical terms here. Or probability mass function. Sometimes abbreviated as p.m.f. So I give an example, namely the number of heads when I toss 3 coins. And I say this is the random variable x that I'm interested in. So my event space, if I toss 3 coins, could be head, 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 or it could be a tail, 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 head, tail, head, tail, head, and so on. I'm not giving all 8 possibilities now. So these are the possible outcomes, and these are now mapped to the possible values. So I'm using a small x to talk about the different possible realizations, and the possible, or the range of this random variable is 0, 1, 2, or 3. So for example, this event here, all tails, maps to the 0. Then this event, all heads, maps to the number 3, and so on. And if I now count how many outcomes map to a given value, I can draw this as a histogram. So overall, we had 8 possible outcomes. 2 to the power of 3 is 8. And here's the probabilities 1/8 or 3/8 respectively of getting these possible realizations for my random variable, namely 0, 1, 2, or 3. Okay, and I'm now writing this in a very pedantic fashion, and I'm doing it just this once. So the probability that any outcome, this is a small omega from my event space omega, I'm interested in all the outcomes that are mapped to a value of 2 of this random variable. So I'm interested in all outcomes that have 2 heads in 3 coin tosses, and in the probability of all that. So this is the probability of having either head, head, tail, or head, tail, head, or tail, head, head in the 3 tosses. This is 3 favorable outcomes out of the total number of 8. And now nobody has time to write such a thing, and this is why people write this in shorter notation. They say that the probability that my random variable x takes the value 2 is 3/8. Or even shorter, I simply call this p of 2. And p is now a shorthand for the probability mass function. So here I've taken a specific example. If I want to talk not about the value 2, but in general, I can say that the probability that x equals x, or xi here, is p of xi. Okay, and I'm writing that down because expressions like this you will often see. And if you see it for the first time, it doesn't make sense. The probability that x is x, it sounds meaningless. But the thing is that the capital X is a random variable, and the small x is the realization thereof. Now these things are normalized. So the sum of a probability mass function must be 1. And yet another sign that people use is the following. In this example that I've shown here, one could say that x, this tilde now means, is distributed according to. And then the most important distributions have a name. For example, this histogram that I've shown here was the probability mass function of a binomial distribution with a total of 3 trials and the probability of success, if it was a fair coin, of 1/2. And just to show you a few more binomial distributions. Here, for example, this histogram would show you if we have 5 trials and if we throw a coin, a fair coin, how many heads will we observe? There is some chance of observing, 5 heads in 5 experiments, but it's pretty low. And here's the distribution. Here, if you toss a coin 15 times, the probability of getting 15 heads, it's larger than 0, but pretty close to 0. It's positive, but very small. And here's the distribution. And you see that as the number of trials goes up, it's a discrete distribution, but the shape becomes more and more Gaussian, even though Gaussian is a continuous distribution. And then if you use more extreme chances of success, so not 1/2, but 0.9, you get a skewed distribution. Okay, and you've seen that before. I just want to relate it to the thing that I've said here. Okay, so that was the definition of a discrete distribution and an example thereof. And next I want to talk about continuous distributions. So a continuous distribution is characterized not by a probability mass function, but by a probability density function. That's often abbreviated as p.d.f. Such that the probability that my random variable x has a realization that's in some domain A or in some set A is the integral over that set over the probability density function. So P now is your probability density function. So as a trivial example, if we do this for the real line, then we have the probability that my realization lies in between a lower and an upper bound A and B is the integral of my probability density function from A to B. And again, this thing is normalized. So if I integrate over the entire line, I must obtain 1. An important technical point is that if we have such a purely continuous distribution, then the probability of the random variable taking on exactly a given value is 0. Even though observation A is still possible, as long as we have positive density there. It's still possible provided that the probability density function at that point is larger than 0. Okay, let me show you some examples of continuous distributions. Closely related to the binomial is the beta distribution. They are related in Bayesian inference. So let's say if I perform an experiment and if I make a total of 40 trials and I found 16 tails and 24 heads, and I want to estimate what is the probability of success, then this blue curve here would show you the probability density function of this unknown parameter that we're trying to estimate. So binomial and beta are closely related. It's a continuous distribution. It only lives on the interval 0, 1, and it's extremely important in the probabilistic methods in pattern recognition. You see that it can take a variety of shapes. So if it has 2 parameters, alpha and beta, if these are very low, it's a bimodal distribution. If both are 1, it's just uniform. And as you move towards very large parameter values, it becomes more and more similar to the Gaussian. We will see this again in certain models. Okay, so I've been sorry, Bernhard. Let's show 1 or 2 more. A generalization of the beta to higher dimensions is the Dirichlet, which lives on the simplex, and well, as physicists, again a discrete one. As physicists, you know the Poisson distribution, and I think these are all I had in mind for now. Okay. Okay, I'll throw some more definitions at you. We need expectation and variance. I think all of you have seen these before. I just want to rewrite it here in terms of this probability mass function or probability density function. So expectation is used to characterize the location of a distribution. So the expectation of a random variable x. If I only have a single random variable here, there's no danger of confusion. If there are several random variables, I could also put the x here to say that this expectation operator refers to that random variable. In the discrete case, it's a sum over all values in the range of xi times the probability that the random variable takes that value. So the probability that x equals xi. Or written in terms of the probability mass function. Okay, so small p is the probability mass function. That's for a discrete distribution. For a continuous distribution, we have an integral instead of the summation. By the way, there are also mixed discrete and continuous distributions, but I'm not talking about these today. So this is the expectation. And we will need those definitions again. The variance instead characterizes the spread of a distribution. And it's defined as the expected value of x minus expectation of x squared. And the better known relative of the variance is the standard deviation, which is just the square root of it. The standard deviation okay. So we have those out of the way, and those you will have known. The thing I want to show next you might not have seen yet. Namely, bivariate and multivariate distributions. I've just shown a picture of a multivariate distribution, namely, the Dirichlet. That was the one that lived on the simplex. I will show it to you in terms, on this one here, in terms of a picture. So here is a random variable, or the probability mass function of a random variable that is shown here in the joint space, or I could show it separately and say this is a random variable x and this is a random variable y, and then what I would have here would be the joint probability of x and y. Okay, so in say this thing here is the joint, and now there are a couple of important specializations. Namely, I can just look at the distribution of the one variable irrespective of the value of the other. Those would be the marginals, and this is what's shown here. So this distribution on the left-hand side has been obtained by integrating out the other random variable. And that distribution has been obtained by integrating out the other random variable. So this would be two marginals, this one and that one. And you see that the probability mass has been conserved. Yeah, so these peaks are pretty low, and by integrating across them, well, I obtain something that looks larger. Overall, the joint sums up to 1, and each of the marginals separately sums up to 1. So let's start with those. So the joint distribution in the discrete case would be the probability that random variable x takes on realization small x and random variable y takes on realization y. And shorthand for this would be p of xy, where p is now again a probability mass function. And because it is a probability mass function, it must be larger than or equal to 0 everywhere, and it must integrate to 1. So if I sum over all possible realizations, x and y, I must obtain a 1. In the continuous case, this is the probability that this pair of random variables x and y takes on values in some set A, and they obtain it by an integration over that set. Where P is now a probability density function. And if A is the entire domain, then again this must sum up to 1. Now the marginals are obtained as follows. In the discrete case, I am interested in P. So this is again a probability mass function because I'm talking about the discrete case. And I can now write this with an index that's a capital X, the subscript here, which tells me that I'm now interested in this probability mass function of the random variable x only. And that is obtained by integrating out the second dimension. Okay, never again in your life will you see this written out in so much detail. So this is the short form that people use, but I'm doing it just this once to be totally explicit. Similarly, in the continuous case, let me delete that after all that I've said before about this technical thing. Okay, and the probability that the random variable is in some interval then, so I integrate from A to B across X, and I integrate across the entire domain for Y. Okay, so I think you understood what joints and marginals were already when I showed you the picture. But for completeness, I've given the formulas. Now there's one more quantity of interest, namely the, let me look for a better pen. So what if I'm interested in the distribution of Y for a given X? So let's say this single row here. That is going to be a conditional distribution. And in terms of terminology, that's the last one, the last element that we need. In the discrete case, it's written as follows. The probability that X takes value as X, given that Y equals Y. So this vertical bar is read as given that. Now, this is related to the joint, but we need to renormalize. You see that these things here, they look pretty low. So if I will integrate along this orange line here, I will not get a 1. And this is why I need to divide by the overall probability, which was shown by this value here. So I divide by the probability of observing that particular value here. So this is just P of Y equals Y. That was a scalar number that I showed here. And you see this whole thing sums up to 1. So this number here is something much smaller than 1. So I divide the numerator by a number smaller than 1, which will make the whole thing larger overall. namely exactly so large that it will again normalize to 1. Okay, we will check this in a moment. But to facilitate the writing, I'm using a more compact notation here by saying that I want the probability mass function of x given y they obtain it as follows. So it's the same thing, just written in a more succinct fashion. And now as regards the normalization, let's look at this. I sum over all possible values x. You see now I've already omitted the subscript because it's clear from the context what p here is. And I'm inserting the definition. But that is just p of y. And hence this whole thing is normalized. So that was the discrete formulation. And then we have the continuous one, where now we have a probability density function p of x given y. It reads just the same as above. So in notation there's no difference, but we know that this was a probability mass function, whereas this is a probability density function. And it's also normalized, so if I integrate over this thing, I get 1. Okay, you have more than earned a break, but before, do you have any questions? Go ahead. I wrote it on the wrong axis. Let's correct for that. If I find my... Thank you. So if this is for a given y, then this must be y, and this must be x. Okay, I've relabeled. Thank you. 2 equations that are extremely important. So should you, God forbid, be run over by a car, then at least you have learned this before. I'm not sure that will help you, but no, seriously, these are equations that govern much of statistics. The first one is Bayes' theorem, and now that we've seen all these things with the marginals and conditionals and so on, it's a one-line derivation. So we have that the joint is the probability of y given x times p of x. And I can write it the other way around as p of x given y times p of y. And now, taken together, I can reformulate this as the probability of y given x being p of x given y times p of y divided by p of x. So now let's fill this with life. Let's say that y is the label and x are the features. Then what we see here is, well, can you try and guess, or can you explain to me what is p of y? Can you put in words what is P of y? Okay, maybe that's asking too much. It is, as it says, it's a probability of y, but the important point is that this is the prior probability of class number y. So prior means before I have looked at the given observation. So let's say you hand me an observation x, and I should make a prediction, and before looking at x, I would predict the more dominant class. So let's say if you give me let's say we're walking around on the street, and you ask me, is this person healthy or not? Well, because most people walking on the street are healthy, I would say that, I would predict the person's healthy. If, on the other hand, we're in an intensive care station, and you ask me, is that person healthy? Before even looking at that person, there might be, let's say, a 1/4 chance it's a doctor, 1/2 chance it's a nurse, but a 1/4 chance it's a patient. So, or if it's a hospital with too few nurses and doctors, and the probability that it's a patient rises. So I might predict that this person is sick. So this is the prior probability of a class before looking at any observations. Now that is the likelihood or the class density. In our case, it is the class density. And this thing here is the posterior probability of class y given the observation x. Oh, sorry, I can hardly read this. It's the posterior probability of class y given observation x. The last thing, the thing in the denominator, is less important for us now. It's the evidence. And if I now have to make a prediction, the quantity of interest is this P of y given x. So I want to know which class is most likely given my observations. And there are now two sets of techniques. Fundamentally, the generative classifiers, they concentrate on the right-hand side. So in generative classifiers, you try and estimate each of these quantities and then plug them into this equation. Where is this? Do we see the screen? Okay, sorry, then I should point around here. In generative classifiers, we try and estimate all these quantities here and plug them into this equation to get out the posterior. In discriminative classifiers, on the other hand, one tries and estimate this quantity directly. And most people now accept this Bayesian paradigm as the proper way to do inference or to estimate parameters, because it allows you to combine a prior expectation with some kind of observation. Okay, and this we can now look at in terms of a picture, which you have, and we will use it in a few moments in statistical decision theory. So all the quantities in the equation is down here, are now given in terms of pictures for a specific example. I have handcrafted this example. So I said that this is the two-dimensional feature space, and I decided that this should be the distribution in feature space of class 1. So that's the probability of being at a given point in feature space if a sample belongs to class 1. It's the same, these pictures look the same. The only difference here is in the scale. Because on the left-hand side, I've multiplied this with the prior probability. I have decided that class number 1 should be more abundant than class number 2. So the probabilities here, I decided that this would be 2/3 and that would be 1/3. Okay, so this thing here is what we have in the numerator. The denominator is obtained as follows. This is just the probability of x irrespective of what class we're looking at. So it's a marginal probability. I can obtain it by integrating out class membership. So in this artificial example, I can obtain that by summing over these weighted class densities. So in other words, this thing plus that thing gives me this picture here, the probability density P of x. And if I now insert all of that into the equation, I can obtain the left-hand side, which is depicted here. So this is the probability of seeing class 1 depending on where I am in feature space, and that's the probability of seeing class 2 depending on where I am in feature space. And these colorful images are perhaps a little bit abstract, so I've also drawn from these true underlying distributions, I've drawn a sample of observations. So I've drawn a training set, if you wish, and you see that the red points have been drawn from this distribution here, the blue points have been drawn from that distribution, and the distributions overlap, but the blue is plotted on top of the red, so maybe you don't see all the red points here. Now, we could use the nearest neighbor classifier on this, of course, but as scientists, we would like to know what is the ultimate best possible classifier. We would all think that the decision boundary must be somewhere here, so we would probably agree that this green line here is not such a bad idea. But what about this? The green line is repeated here. How about this small appendix or this small island? Would we not prefer to get rid of it, or why should it be there? And so in pursuit of this best possible classifier that exists in the whole world, is in pursuit of this elusive quantity that we're now talking about statistical decision theory.